Hi everyone. In this video, we'll understand what is flotation and what is metacenter, how actually the metacentric height is determined analytically as well as experimentally. See, in the previous videos, we have understood what is buoyancy and how the buoyancy force is calculated in case of submerged condition. But during the floating condition, what will happen? Let me explain with the sketch. So you consider a body, okay, which is floating in a liquid. So this is the liquid surface. So you consider this as the normal axis or the longitudinal axis of that body. I'll consider it as normal axis. Okay. So this is the center of gravity where the weight of the body is acting. Okay. So now consider the center of buoyancy where the buoyant force FB is acting. Now, what we do is we give an angular displacement or oscillation to this body in the clockwise direction. So if I give an oscillation like this in the clockwise direction, now you observe this is the liquid surface what we have. This is the normal axis. So we have given the angular displacement in case of what? In the clockwise direction. This is our normal axis. Okay. So this is the point that is center of gravity where the weight of the body is acting. Correct? Since the body is oscillated, you observe the center of buoyancy will also shift. Why the center of buoyancy will shift? Because here you observe this is the depth of immersion. Since we have given an oscillation in clockwise direction, the body is tilted and the volume of the immersed part changes. As the volume of the immersed part changes, the center of buoyancy, which was earlier at the point B, will shift to the new point. Let me take this point as B1, where this is the point of the force of buoyancy is acting. Okay, so because of the tilting, the volume of the immersed part changes. Because of that, the center of buoyancy also shift to the new position, that is point from point B to B1, where the force of buoyancy is acting. Now you extend the line of action of this buoyant force where it meets the normal axis at point M. This point M is called as metacenter. Okay, so what is metacenter? It is the point of intersection between the line of action of the buoyancy force and the normal axis. So this point is known as metacenter. This metacenter plays a very important role in case of the floating bodies. Now you observe this point G and this point M. That is, point G is the center of gravity. Point M is metacenter. The distance GM, the distance between the center of gravity of the body and the metacenter, is known as metacentric height. Is known as metacentric height. Okay, understood? So now we'll see how this metacentric height, that is GM, is found out both analytically as well as experimentally. Now we'll see how to find the metacentric height analytically or theoretically. So I considered the same figure, that is a floating body. So where this is center of gravity, center of buoyancy, where the force of buoyancy is acting. This is where the weight of the body is acting at the point G. AB is the free surface of the liquid. Now I give an clockwise rotation for this body. Because of this, the body will oscillate. Now this was the AB was the previous free surface. Now it has changed to A dash, B dash. Okay, now because of this tilting and the volume of the immersed part changes, your center of buoyancy also changes to the new point B1, where this force of buoyancy is acting. Now we extend the line of action of this force where it cuts the normal axis, is called as metacenter M. Okay, so theta is the angle of inclination, that is the angle of oscillation what we have given. So this is theta. So this surface AB was the original surface, A dash B dash is the new surface. This angle is also works out to be theta. Correct? This angle is also works out to be theta. Now what I do is I consider a triangle. I consider the triangle B, B1, M. Then I'll apply tan theta for this. Tan theta is equal to opposite, that is B, B1 divided by adjacent side, that is B, M. Therefore, B, B1, which is given by Bm into, what I'll do is for the small angle of theta, because since the oscillation given is very small, this theta, I tan theta, I'll take it as theta. I'll keep this on this side. Now, due to the shifting of this center of buoyancy, this force Fp will form an couple. Okay, so this force Fb will form an couple. So that is couple due to the shifting of the center of buoyancy. Couple due to the shifting of the center of buoyancy from point B to B1. Okay, couple due to, I'll write couple due to the force Fb directly, which is this couple is formed due to the shifting of the center of buoyancy from point B to B1. Correct? This is given by, couple means force multiplied by perpendicular distance, that is BB1, Fb into BB1. But we know that this Fb into BB1 is what? Bm into what? Theta. Bm into what? Theta. But we know that in case of the floating condition, this force of buoyancy is nothing but the weight of the body, that I'll take it as W into Bm into theta. This weight W is nothing but density multiplied by volume into what? Bm into theta. Call this as equation 1. So I have used here V dash. V dash indicates the volume of the immersed part of this body. Gamma means density. V dash is volume of immersed part. Bm is the distance, center of buoyancy and metacentre, multiplied by theta is the angle of oscillation. This value is nothing but couple which is formed due to the shifting of the center of buoyancy from point B to B1. That is coupled due to the center of the force of buoyancy Fb. Correct? Now what I'll do is I'll consider a small elemental strip. I'll consider a small elemental strip of thickness dx, at a distance x, from the normal axis. I'll consider an elemental strip on both the side. I'll consider the elemental strip of thickness dx at a distance x, okay, from the normal axis. On either side, the distance is x only. Okay, so I'll consider a small elemental strip on at a distance x from the normal axis. The thickness is dx. So if I take the plan of that at the intersection of the liquid, or I'll take the plan of that this body at the liquid surface, I'll get, I write the plan here. Okay, so this is the longitudinal axis or y axis. So I am taking the plan of this. Plan means the top view at the free surface of the liquid. I'll take, if I write this dx will be longitudinally like this, that is elemental strip completely on either side. This at a distance what? X. The thickness is, I take it as dx. L is the length of this strip. This I'll call it as figure C. This is figure B. This I'll take it as figure A. Okay, so figure C represents what? This plan at the liquid surface, the plan of the body at the liquid surface, where this The small elemental strip I have taken at a distance x from the longitudinal axis. The dx is the thickness of this strip, then L is the length of the strip. Okay, you understood? Now what I'll do is I'll consider this small strip. No, so I'll calculate what is the height. This height of the strip is what? This height of the strip, what we have taken is nothing but x into theta, because this angle is theta, this angle is also theta, distance is x. Therefore, this height works out to be what? X into theta. Now, what I'll do is I'll take the volume of this strip. First, I'll take volume of strip. What is the volume of strip? Area multiplied by this area multiplied by length. What is the area? This height. Okay, this height multiplied by thickness. What is height? X theta into what? Dx is the area multiplied by the length of the strip will give what? Volume of the strip. Next, I'll consider the weight of the strip. I'll consider this weight of the small strip, which is equal to density multiplied by volume, that is x theta into dx into what? L. Correct. Now, at this small elemental strip also, the force of buoyancy is acting. This is, I'll take it as dFB. The force of buoyancy here is acting downwards. This dFB is what? It is the force of buoyancy acting on the small elemental strip. Since this elemental strip is very small, I have taken as dFB. dFB indicates the force of buoyancy due to this strip, which exerts on both the strips. Okay. Now, this force of buoyancy, dFB, which is equal to the force of buoyancy to the strip is equal to the dFB, which is nothing but the weight of the strip. Or else I'll write this weight of strip is equal to gamma into x theta into dx into L, which further equal to the force of buoyancy due to this small elemental strip. Force of buoyancy due to the small elemental strip. Now, couple due to this force of buoyancy dFB, that is couple due to this force of buoyancy elemental strip, which is given by dFB is given by the force of buoyancy dFB into the distance. What is the distance here? You observe. This is x. This is one force of buoyancy. This is another force of buoyancy acting downwards. The distance between these two equal and opposite forces is what? 2x. I'll write 2x is the couple which is formed due to dFB. Now, what is dFB? I substitute gamma into x theta into dx into L, that multiplied by 2x. Okay, which is equal to gamma into 2x square into theta into dx into L. Okay, but you observe this dx into L. This dx thickness into the length L is nothing but the area. Okay, this area of the body at the free surface of the liquid. So I'll denote this, I'll take the area as dA. Therefore, this couple will form due to this works out to be gamma into 2x square into theta into what? Area dA. dA represents the area of the body at the liquid surface, which is further equal to dx into L. This is couple which is formed due to what? dFB. Now, I'll consider. So this is couple formed due to the dFB. I need couple which is formed due to only the FB, that is the center of buoyancy, means I have to integrate this equation. If I integrate that equation, I'll get this. So couple due to dFB means if I integrate this again, it becomes couple due to FB, which is equal to integration of gamma into 2x square theta into what? dA, which is equal to gamma is constant. I'll take outside. Theta is also the angle of oscillation. The remaining is 2x square into dA. So this 2x square into dA, I'll take it as this nothing but gamma theta into I. What is I? I, which is equal to integration of 2x square dA. Okay, so that I represents moment of inertia of the plane area at the free surface of the liquid. You can refer the figure C for that. So what is I? I represents the moment of inertia of plane area at the free surface of the liquid. By using this refer C, it becomes Iy. We have to take the moment of inertia at the longitudinal axis. Okay, now this is coupled due to the force Fp again. Now you observe equation 1 and 2, equating equation 1 and 2, we get gamma into V dash into Bm theta, which is equal to gamma theta into what? I. With gamma theta and this gamma theta cancel, this Bm distance works out to be moment of inertia divided by V dash. V dash is what? Volume of immersed portion. This is the distance Bm. Okay, but I need the metacentric height. What is the metacentric height here? That is Gm represents metacentric height. You observe this sketch and you observe that Gm is equal to this Bm minus Bg, correct? So therefore Gm is equal to what is Bm? I divided by V dash minus of Bg is the metacentric height formula. So here you observe Gm represents metacentric height, I represents moment of inertia of plane area at the liquid surface, refer this figure C. Then V dash is the volume of the immersed portion of the body minus this Bg. Bg represents distance between the center of buoyancy and the center of gravity, this Bg that you can get. So this is how you can find the metacentric height analytically. Now we'll see how the metacentric height is determined experimentally. Okay, so experimental determination of the metacentric height. You consider a floating body. So I'll consider an floating body. So this is the normal axis of that body, which was floating in the liquid like this. So this is the center of gravity. This is the center of buoyancy. Both are lying on the normal axis. Now I place small weight. I place the small weight W1 on top of the floating body. Okay. Now what I do is I just move this small weight W1 to the right side of this or to any one side. I'll move this weight. If I move this weight to any one side, this body will be tilted in that direction. Correct? If I move this to this side, this body will be tilted clockwise. So if I move that, you observe this. Okay, this is the axis. Now this body is moved to the end. This is having a weight W1. The distance over which it has moved, I take it as X. Okay, so this works out to be the normal axis. So this is the free surface of the liquid, correct? Now this was the center of gravity earlier. This is center of buoyancy. Okay, now you observe, since the weight has been moved to one side, okay, this center of gravity also shift to the new point, because we know that center of gravity is the point where the weight is acting. Since the weight has changed, this center of gravity will also shift to the new point. And as the body is tilted, the volume of the immersed part changes. Therefore, the force of or the center of buoyancy will also changes now. this center of buoyancy, I'll take it as B1 is the new center of buoyancy. G1 is the new center of gravity. Now, I'll extend this force of buoyancy. Okay, you observe to the point where it meets the neutral axis is what? Metacentre M. So this angle, I'll take it as theta. This angle, I'll take it as what? Theta. So now you observe this angle theta, or the angle of tilt, is measured, okay, from the plumb line and the protractor attached to the floating body. Because since it is experimental termination, we have to calculate the theta by the plumb line and the protractor which was attached to the floating body. Correct? So you understood why the center of gravity changes, because the weight as in moved to the at a distance x. Then center of buoyancy changes because the volume of immersed part changes. Correct? So this point is G1, this point is B1. Now you consider this triangle, that is G1M. You consider the triangle G1M. You apply tan theta, which is equal to opposite side G1 divided by adjacent side GM. Therefore, G1, which is equal to GM into what? Tan theta. You keep it on one side. Now, since the shifting of the weight to the one side, the moment will be formed to this. Moment will be formed due to this weight W1. I'll write moment due to weight, small weight W1 is given by W1 into what? Perpendicular distance, that is X. Okay, so you call this as equation 1. Now, one more moment will be developed. That moment will be developed due to the shifting of the center of gravity from the point G to G1. So one more moment will be developed because of the shifting of the center of gravity, that is moment due to shifting of CG, that is center of gravity, which is given by the weight of the body, because the weight also changes here. That is because the center of gravity means it's the point where the weight is concentrated. Therefore, that weight multiplied by the distance GG1. Okay, but what is GG1? Already we have written here, that is W into GM. GG1 is nothing but GM tan theta. Call this as equation 2. In order to achieve an equilibrium, the one moment which was acting, that is W1 into X, the another moment is WGM into tan theta. So in order to achieve an equilibrium, both these moments should be same. Therefore, I'll equate both the moment, that is WGM tan theta is equal to W1 into X. Therefore, GM is equal to W1 into X divided by W and theta. Okay, so this is how you can determine the metacentric height experimentally. Here, this W1 is the weight of the small weight which was placed at the top of the floating body. X is the distance with which the small weight is moved. Capital W, here this is very, very important. Capital W includes the weight of body plus W1, that is the weight of the small weight. That is capital W is equal to weight of the body plus W1 is what? The capital W. It is a total weight, including all the extra weight it is on the floating body. That is a total weight. Therefore, GM is equal to W1 into X divided by W tan theta. Okay, kindly go through this determination of metacentric height, understand it properly. Okay, thank you all.